Welcome to our first video in the series on metabolism. In this video, we'll introduce many terms that will be helpful as we move through this unit on energy transfers in living systems. We will learn how to evaluate reactions to determine if they are energy absorbing or energy releasing, building or breaking down molecules, occurring spontaneously, or if they need a nudge. But let's start by defining metabolism. The process by which energy is acquired and converted through the building and breaking apart of molecules to store and release energy in a controlled manner. Let's think of the body or even a cell as an engine. The engine needs fuel. This gasoline represents a great deal of energy. However, we need to release the energy in a controlled manner. We certainly don't want to release all the energy at once. We need to take the energy out and manageable size it and use it bit by bit. And cells and bodies need to be able to do the same thing with their energy. But what is energy? Energy is the ability to do work, and it comes in many different forms. We're going to focus on energy in kind of two broad categories to start. Kinetic energy, which is the energy of motion, and potential energy, which is stored energy. Like water behind this dam, it has the potential to do work. Potential energy can be converted into other forms of energy. The water moving through this dam is used to produce hydroelectric power. And if we look at this roller coaster, I'll bring this over. At the top of this roller coaster, the body has lots of potential energy, and as it moves down, that potential energy becomes kinetic energy. If we look at this picture, this ball is sitting on the ground. It has zero potential energy and it's not moving, so it has zero kinetic energy. But as I move the ball up to this step and it's not moving, it has potential energy but not kinetic energy. If it rolls off, that potential energy is converted into kinetic energy, and the higher step that it's on, the more potential energy it has, and as it goes down, that potential energy is converted into kinetic energy. Let's take a closer look at potential energy on the atomic and molecular level. Where in an atom is there energy? Well, we recall that electrons spend their time spinning around the nucleus of an atom, and they do this at very distinct energy levels. An electron at this energy level has less energy than an electron at this higher energy level, and less than one at this outer energy level. So the energy level, or the ring that electron occupies, represents the amount of energy that electron has, and the fact that it's moving is energy. These electrons can absorb and give off energy. For example, if a photon of light came in and struck this electron, that electron might jump up to a higher orbital. But often these electrons don't stay up there at this energized state. They will quickly fall back down, returning to its ground state, and when it does, it gives that energy back off, often in the form of light or heat. And it gives it off in a very specific amount. We know also that energy can be stored inside of molecules. This is an atom, but inside of a molecule, where would the energy be stored? If we look at this equation, we see that whatever molecule A is, molecule A, if we go in this direction, breaks apart into molecules B and C, and we have this energy. And the question is, where did that energy come from? And we know it has to come from inside of A. And so if maybe A is, we can draw it like this, there's molecule A, and then this is B and C. The energy was found in this chemical bond, held up in that bond. And we know that these bonds, we can break these bonds to release energy. So we have potential energy stored in chemical bonds. We call it chemical bond energy. When these bonds are formed or when they're broken, energy can be trapped in these bonds or released from them. Before we go any further, let's discuss two important laws that govern energy. The first law of thermodynamics and the second law of thermodynamics. Now this first one is probably familiar to you, and it states basically that we can neither destroy or produce energy. All the energy that we have before, we're going to have after. Energy cannot be created or destroyed, and that's the first law of thermodynamics, and that's going to govern kind of how we watch how energy flows through systems. And the second law of thermodynamics explains the natural progression of energy states. It says that energy is always moving from higher energy quality forms, or higher quality energy forms, to lower quality forms. A low quality form of energy would be something like heat. And that no conversion is 100% efficient. That entropy is always increasing. A system will spontaneously become more and more disorganized. Every energy transformation or transfer increases the entropy of the universe. So entropy is the measure of a system's disorder, and it's always increasing, or its natural tendency is to increase. In other words, if we have molecules that are organized like this, it's their tendency to move in this direction to become less organized. In order for us to go in the opposite direction, we'd have to spend some energy. I want you to think about entropy this way. If you clean your room like last week, by the end of the week, I suggest that your room's probably messy again. But I don't think you recall intentionally making your room messy. It just kind of happens. It's entropy. Things become more disorganized. But interestingly enough, your room never cleans itself. It never orders itself. Things don't have the tendency to go in this direction. They have the tendency to go in this direction. It'd be nice if my room would actually clean itself, but it's not likely to happen. Armed with this information, let's evaluate some reactions. We want to determine if they're either endergonic or exergonic. Meaning, do they take energy in or do they release energy out? You may have heard the terms endothermic or exothermic. This is very specific, thermic being a type of heat, type of energy, meaning heat. Endergonic, exergonic, more generic. Gonic meaning energy. So energy in, energy out, heat in, heat out. We also want to be able to categorize reactions as anabolic or catabolic. Anabolic reactions build and catabolic reactions break down. So you can think of building and digesting. And while we look at these issues, we can possibly predict if these reactions will occur spontaneously or not. And finally, we may have time to talk about energy coupling. If we couple or pair an exergonic reaction, a reaction that releases energy, and couple that with a reaction that's endergonic that requires energy, we see that one of these reactions could drive the other. One of the tools we use to help us visualize what's happening in a reaction is called a potential energy diagram. It allows us to graphically depict the changes in energy during the course of a reaction. And finally, to evaluate a reaction, we'll use an equation called Gibbs free energy equation. We're going to measure the free energy, the energy available to do work. And the equation is delta G equals delta H minus T times delta S. So what does each of these elements mean? Well, G represents Gibbs free energy, or the energy available to do work. I want to look at the change in the G. H represents the total energy. T is temperature, but we've got to do it in Kelvin because we don't need any negative values. And S is a measure of entropy, so we're going to try to measure a change or delta entropy. Now, the delta H and the delta S are difficult numbers to come to exact values for, but luckily we don't need the exact values, we just need to know if it's a positive or negative number. We can use this equation to determine whether a reaction is spontaneous or not spontaneous. All we need to know is this: what's the value of delta G? Is it a positive number or a negative number? A reaction will be spontaneous if the change in the free energy, delta G, is negative. It's probably best if we just work some examples. Let's start with this example. Let's just generically say A yields B plus C plus energy. Let's look at what that looks like on a potential diagram. We know that energy is coming out, so whatever value A has, we don't need to know the exact number, that say A has this much energy. We know that B plus C have to have less energy because this energy goes away. So the shape of this graph is going to look something like this. And the energy that's given off, we can represent here. That's this energy. Now, when we look at this reaction, we got to categorize it as endergonic or exergonic. Well, we could look at the equation, and energy is exiting the arrow, so it's an exergonic reaction. That's one way. If you just have the equation, look at where energy is relative to the arrow. If energy is going into the arrow, it's endergonic. If it's going in, if energy is coming out, it's exergonic. We can also look at the graph. In the graph, think of this like a fuel gauge. We're here, and we have less gas in our tank now. We've dropped down to here, so energy must have exited, exergonic. So this reaction is exergonic. But the next question is this reaction going to occur spontaneously or not? Well, let's look at Gibbs free energy equation. Now, for this reaction, the delta G, whoops, I can't use a black pen, delta G equals delta H. Well, the change in energy, the delta H, we can see in the graph is a negative value. Energy, we went from here down to here, so that's negative delta H. So, this is a negative number. Minus the temperature. Well, the temperature is in Kelvin, so it always has to be a positive value. And the delta S. What happened to entropy? Did it increase or decrease? Did we get more or less organized? Well, let's think about it. We had one molecule A, and now we have two molecules B and C. We went from one piece to two. I would say that's entropy increasing. We're becoming less organized. So entropy increased. So what is the value for delta G? Well, delta G equals a negative number minus two positive numbers. A positive number times a positive number is always a positive number, and a negative number minus a positive number will equal a negative value. So delta G is negative, which means this is a spontaneous reaction. Let's do another one. In fact, we'll start over and just turn this equation around and look what happens if we have the reverse of this equation. So, instead of A breaking down into B or C, what happens if we have molecule B plus molecule C plus the energy to make molecule A? What happens to our fuel tank? Are we putting energy in or taking energy out? We know that this energy that's here has to exist on this side because of the law of conservation of energy. So this energy must be inside of molecule A. So that the value for A, as the reaction progresses, we have B plus C. We're putting energy in, and we eventually have molecule A. So the energy inside of molecule A has to be greater than B plus C because we are adding energy. This is an endergonic reaction. Now let's look at Gibbs free energy equation to determine whether this reaction would be spontaneous. Well, delta G in this case equals delta H. We're putting energy in, we're putting fuel in the tank, so delta H is a positive number. And we know that temperature in this case is Kelvin, so it's always a positive value. And entropy, the measure of a system's disorder, we're going from two parts to one part, so we're increasing or we're decreasing entropy, we're decreasing disorder, we're becoming more orderly. So the delta S, the change in disorganization, is a negative value. We have negative entropy. So what does this mean mathematically? If I can scroll down, that means that we have a positive number times a negative number is always a negative number, and we subtract a negative, that's like adding a positive, so we have a positive number plus a positive number, and so the value for delta G has to be positive, which is a non-spontaneous reaction. Now if you just look at the shape of this graph and we think about putting a ball here, is that ball going to roll up the hill spontaneously? Probably not. But when we look at this reaction, if we put a ball here, is it going to spontaneously roll down the hill? And the answer is yes. So that kind of visually helps us to decide. Let's look at two more. How about this reaction? A plus energy yields B plus C. By this time, we should know that this reaction is going to look this direction because we're putting energy in. We're going from A to B plus C. What does that mean for the Gibbs free energy equation? Well, let's see. Delta H is going to be a positive number because we're putting energy in. So I'll just make that a positive. And the temperature is always positive because it's in Kelvin. What about entropy? Entropy is increasing because we're getting less organized. We're going from one thing to two things, so entropy is increasing. So positive times a positive is a positive. And so the question is, what is the value of delta G? Is it negative? Well, in this case, it depends. It depends on how big or what the value of this number here is? And that depends on the temperature. Delta G will be negative, which means will be spontaneous at high temps. I'm going to leave you with the last one to work out on your own. B plus C yields A plus energy. I want you to tell me or draw for me the shape of the graph, determine if it's endergonic or exergonic, and using Gibbs free energy equation, under what conditions could this reaction occur spontaneously? In class we're going to talk about equilibrium and metabolic disequilibriums. What happens when these reactions are reversed, and when do they go in which direction, because most of these reactions are reversible. And come back for the next video where we're going to discuss enzymes and how they affect the rate of this reaction.